evening, and once again, welcome to the Young Modular Solution. So, like I promised in my introductory video in this practical solution series, I promised to um, explain all the practical that you'll be doing for this first semester. All right. For those that are using the manual that is currently on, let me show us the very manual that we are using. Today is 4th of March 2024, in case you are seeing this video after this very year. So the manual that I'm working with is this very one here. Okay, and well, the cover may not be the same, but you can see the experiments. Experiment M9 is what I'm going to treat tonight. Don't forget that the particles are randomly selected or given for each group. Okay, so I'll be taking the practical solution randomly, and like I promised, at the end I'm going to finish all of them. Is that okay? So I'll go straight to what I have today on my the cam scanner, which I used to prepare the PDF of the solution. So I believe that by now you must have gotten the solution material. If you don't have it, you can join the WhatsApp group 09157 293443. So you can chat me up and then join the WhatsApp group as I explain them or as I give you the solution material. Okay. Like I said, I'm going to 9 as we already have it here. I'll be explaining briefly how the experiment will go or should go, and then basically the solution. That is where I'm much interested. All right, now okay, so now you can see you are M9. The title is supposed to be, actually the title they are putting in this very manual is not well placed. That's where the topic or the topic or the title of this experiment is supposed to be Hooke's law. All right, while the aim is to verify Hooke's law and to show how the period of oscillation of a loaded spring depends on the load. Now, if you look at the theoretical background, it is very, very important, and that's why you are always encouraged to go through your practical manual before going to the lab. Is that okay? So the theoretical background is that you must know what Hooke's law is or what Hooke's law holds, and then the application too is exactly what we are trying to demonstrate in this very experiment. A very simple one. Now, first and foremost, you need to understand that Hooke's law relates the force or the load applied to an elastic material and then the extension produced. And we know that when you keep increasing the load or the force, the extension also keep increasing in that order. All right, in that order. Precious. Che, I'm on live video. Please just enter. Go to the room, abeg. Is it locked? Yes. Hey, wait. Please, just give me a few minutes. Yeah, go. Yeah, just yes, I'm on live video now. Okay, sorry for that. Okay, so the setup is very clear, and the apparatus we have there, you can see the spiral spring and slotted weights. That is the weights that will be given to you from 50 up to 350. Then the meter, which you can see there, and then stopwatch, which is used for your timing, or stop clock, the clamp, rector stand, and then the optical pin that will be used to denote your length measure. Okay, your extension and the rest of them. All right, so I'm trying to slide to the next page. Okay, sorry for that. Okay, so the background equation, they are all given down there, so you can go through them at the end of the day through your manual. That's not my concern for today. The methods are also given there, but I'm going to summarize that in this video. The method, you can go through it. With the method, you can set up the apparatus, the apparatus, and then do the experiment without any stress. Okay. Now, if you go through the methods, you see they say set up the apparatus as shown in the figure, and then record the pointer reading p-notes when there is no mass added to the scale pan or hook. So that's the first thing you do. All right, so you look at the scale pan and then the hook. So before you add the mass that will be given to you, you just hang the spring and ensure that you record the p note, that is the original length, and that original length will be kept constant all through the experiment. Now you know that there's going to be an extension produced because the spring itself has its own what we call the sprung weights. Okay, but in this experiment, in the course of doing the experiment, we are not going to be adding the weight of that spring into the masses that will be given to us, or the weights that will be given to us. But at the end of the day, we are going to see the effects of that spring weights or the spring mass on this very experiment. So for now, the spring weight is assumed to be negligible. By the end of the day, we are going to account for it as we move on into the main work. Then method 2, now load the scale pan with a mass. The first mass there is 50 grams. Read and record the pointer reading on the meter rule. Then calculate extension E equals to what? P minus P naught. So you can see that, sorry, you can see that based on Hooke's law, by the time you apply you actually add a mass of 50 grams, there's going to be an extension produced. Okay, so the extension produced, or the distance moved, is P, while P naught is original distance when there was no mass attached. So for it to get extension, of course, you have to subtract the final minus what the initial, which is the P minus P naught. Now this experiment is 2-in-1. All right, it's 2-in-1 experiment. You do the Hooke's law verification, go back again to the title, or they call it title, but it's supposed to be the aim. Yeah, you are going to do the Hooke's law verification, and also you are going to also look at the oscillation of that very loaded spring. So if you look at stage 3, or the method 3, it says slightly displaced the scale pan. Okay, let me zoom it. Slightly displace the scale pan vertically downward and let it oscillate about a mean or equilibrium position. Time, okay, 20 oscillation, and record the corresponding time from your stopwatch. Then repeats the experiment for other values of M, 100, 150 up to 350 grams in each case. Okay, and know the pointer reading and the rest of them. So after you must have done your Hooke's law verification, the next is for you to now displace, tilt or displace, just drag the mass downward. Of course, the spring will be moving, will be dangling up and down like that. Of course, you do that for 20 oscillation, just like the way you do your pendulum experiment. Okay, so you can see the equations are all given or stated there also. All right, so we come to the table of values. So how do we fill a table of values? Now on the question, on the part 6 here, it says calculate the extension E equals to P. That's supposed to be P minus P naught. Okay, and not P I equals to P naught. And then the period T, capital T, and then T squared, then tabulate your reading. Now it's a very simple one. The table has already been given to you. You just wait to fill your value. So the first part is where you have your masses, and the masses, or what the weight, the load that was given to you. All right, standard weight that were given to you from 50 grams up to 350, sorry, 300 grams. Now P is your extension, the length or the extension you have when you put your mass of 50, and then You can see the value there. For 50 grams they have 55.1, for hundreds they have 57.0, for 150 they have 58. Of course it must be increasing, and that's why you need to understand the principle behind this very experiment, or what we call a theoretical background. Yes, the length must be increasing. If the length decreases or varied, then that means that the spring has lost its elastic property or its elasticity. All right, so it must be increasing in that order. Now though the person that I'm using, trying to use work, did not record his original length. Okay, but from what we have here, the next column says E in cm. That is supposed to be small e and not capital E. So you have that up there. So by the time you subtract your P from your P naught, or your P naught from your P, you are going to get 2.2. So meaning that the P should be around 53.2. Yeah, if you check the mathematics, because we have the 55.4. So if you subtract 55.4 minus 53.2, you are going to get 2.2. So try that also for the other one. You also get that value. That is how to get the E column, which the extension column. Like I said, that is supposed to be small e and not capital E. All right. So now, just like what I explained earlier, the P and the E section is to verify Hooke's law. Then if you now move down again, you see T1 and T2, then T main, T and capital T. That is the second part of the experiment, where you were asked to displace it at a very small angle so that the system is going to, the loaded mass system is going to vibrate or oscillate vertically, okay, in that order. So that is where we have the T1, T2, and then the T main. So that means we are going to do, for each mass, we are going to do it 2 times. Like I've told us earlier, there are simple way you can also get the timing without going through all the rigorous process. All right, so we quickly move on to getting the mean. Of course, getting the mean is you add T1 plus T2 divided by 2. That is the mean. Then how do you get the capital T? The capital T is divide this T mean by number of oscillation. And in this experiment, we have 20 oscillations. So if you divide your 6.55 divided by 20, this is what we are going to get, 0.828. Okay. The same thing too. If you divide 0.05 by 20, you get 0.103. And of course, you square that to get the other part of the column. So this is how to go about the experiment, a short overview of the work, and then possibly the how to also fill your table of value, like we said earlier. All right, now we'll now come to the part where you have the questions. Okay, where you have your questions and the answers, and that is the part where my solution comes in now to guide you on how the work will look like. Okay, so now the first question is question 1. Plot a graph of M versus or against E, starting from the origin, and calculate, of course, the slope of the graph. Calculate the slope of the graph, which is called S1. Take notes, the slope of the graph here should be called S1, S subscript 1. Then B, plot another graph of M against T square with this as the origin. Then determine the slope S2 and then the intercept I. That thing is not T, it's I, intercept I. It confuses students most times. Calculate the intercept I. Okay, so then now these are the areas I want to make corrections. These are the areas I want to make corrections under 1C. 1C says pi equals to S square over S1. That's not correct. It's supposed to be lambda. You know lambda equals to S2 minus S1. That means lambda is dividing slope 2 by slope 1. You have your lambda. Then we now have n equals to 4 pi square lambda and not 4 pi square r. So make sure you correct that in your manual. Okay, 4 pi square r. Oh, sorry, 4 pi square lambda. So whatever thing you are going to get in this S2 over S1, that becomes a lambda, and you use that to multiply by 4 pi square. Is that okay? All right, so when I move down to the solution page, you are going to see how I actually arrange everything. Okay, then they now said compare your value of n with A equals to 980 and state the difference. Now by the time you get your n from this very question of question 1C, you notice that the n is going to have a value that will be close to 980, maybe 950, 960, 970, 1000, as the case may be. So I'm going to explain what that actually means, okay? And then state the difference. So you say the difference, you're like subtracting this from this, and then that's all. Then state 4 precaution you needed to obtain accurate results. We'll look at all those terms. Just trying to read the question so that we'll be able to get familiar with actually what we are going to be expecting at the end of the day. Then state, okay, they repeated the same thing there in question 2. Question 3, what does your value of I represent? Your value I, which is intercept, represents. Then calculate the force required to expand your spring a distance of 10 cm. Then finally, show that the total energy of any vibrating object is proportional to the square of its amplitude. Okay, quickly we'll move to the solution page now. Now you can see, like I said earlier, this material is to guide you on how to do your job based on what you have. So I started by saying, note, the two graphs are to be plotted separately, not together. Please let's understand it, because this is like unlike M10, where we treated a cantilever beam. Okay, on that cantilever beam, we expected to plot the two graphs together. The essence was to compare when the meter was projected 60 cm and that of 40 cm, to look at the slope of the two graphs. Okay, just to draw a direct comparison between these two setup. All right, but here the graph is expected to be plotted separately. Okay, the graph is expected to be plotted separately. That's what I put there, because most students don't really get that very clear. So the nature of the graph. So the first graph is a graph of M against E. All right, and this is the nature of the graph. Okay, so this is the nature of the graph. I'm sorry, this is supposed to be origin 0, 0, not 0 over 0. Okay, so a graph of M versus E, and of course the unit must be there. Then the next thing, of course, is you have to state your scale based on your value. Now, from what has been done and what is expected to have, the slope S1, which we're told to write, is S1 equals to change in M against change in E. So we now say let S1 equal to 16.67. That means I'm assuming that after plotting the graph and I got a slope of 16.67 gram per cm, the unit is gram per cm, then what are we expecting to get at the end of the day? So this is just a guide. So you plot your graph, get your S1, and then follow me with the work. Then for graph 2, which is a graph of M against T square, this is the nature of your graph. Now we have to be very, very careful in this graph too, and that is the more reason why you need to have the solution to this very material, and not just that, have a guide. Okay, just like this, the video, and then someone to mentor you before you make any move in plotting your graph. So now in graph 2, you have to be very careful, because the slope, sorry, the intercept is going to be on a negative M axis. Yes, we are going to see that in our equation transformation, how the intercept should be, or where the intercept should be. Now what you need to understand is that every practical or every graph you plot has a physical equation that relates the variables concerned. Very, very important. So by the time you compare those equations, the equation of a straight line, you'll be able to draw conclusion on the nature of the graph, where the intercept is going to be, how the slope is going to be. Is it going to be negative? Is it going to be positive? Is it going to cut on the y-axis or on the x-axis, and the case, just like that. So the equation gives you an overview or a summary of how the graph will look like. Okay, so we'll get to that under, I think, question number C or D. Okay, when we get that. So the slope is there, change in M again, change in T square, don't forget. So we then assume that our slope there, S2, is 352 grams per second square. So the intercept, I said, is negative, must be negative. Okay, I say make room for negative axis of your graph, call for explanation. That means if for those who are not going through this video, then they need to call for explanation, and then to also get that. However, like I said, you can also join the WhatsApp group to also have access to a live session, and then ask questions to real humans, and then get solutions to your problem. Okay, so now let's go back to question C. Don't forget that question C. Don't forget that question C that says find lambda, which I corrected from pi to lambda, S2 over S1. So we look at the solution here. So what they mean is that divide your S2 by your S1. I believe with all the things I've said earlier, this part should be very easy for anybody to work on. So that is S2 over S1, not S square over S raised power 1. So it's S subscript 2 over S subscript 1, which is 352 over 16.67, which is slope of the second graph against the slope of the first graph. So if you do that, you are going to get 21 centimeter cm per 21 centimeter per second square. And then when you now put into your lambda, into your n, you get 4 pi square lambda. Say not this equal to 4 pi 4 pi 2r as they stated earlier. So I've already make those correction earlier. So if you check upstairs, if you multiply that, okay, 4 pi square by 21, when you check down here, when you check down here, 4 pi square times 21, you get 829. All right, down the page there, 829. Now if you come up there, you will see, let me drag this icon down here. When you go up there, you see D. They said we should compare. So our n equals to 829, our a equals to 980. Then difference 980 minus 829. Now let me explain what that a actually stands for. That a is just like your acceleration due to gravity. All right. Yes, acceleration due to gravity is 9.8 meter per second square. But when you convert that to centimeter per second square, that is multiplying by 100, you'll be getting 980. So 980 centimeter per second square. That is exactly what you get there. So now the unit is not included. So take note, when you are doing your calculating your lambda is not having unit. I just included that unit so that you're able to have idea. I'll be able to explain some concepts to you. All right. So another tip again I want to give you is that for you to have your lambda to be close to that like your lambda to be your n to be close to that 980. Okay, your lambda value must range from that 20 to 25 or 26, from 20 to 26, so that your value will be close to that a. If I've actually done experiment on M4, I think I mentioned that also, but I'm still going to mention that when we get to M4. All right, so that is that. So I think that is that for the whole thing. Now, under question 2E, we have precautions. So you can see the precautions there. You can check them out and then check your own too. The spring was not stretched beyond its elastic limits, and of course the time you were prompt in taking your timing, stopping the stopwatch at the right time, and then you ensure that the object, the bulb, or sorry, whatever, the spring was released at a very small angle. All right, so that the system oscillates in a uniform manner. So there are other precautions which I stated also in M4. So you go to M4, check the video on M4, and then go through the video or the materials on M4, and then check the experiment precaution that we have that they are similar. All right. Come to question 3, and where they say the question 3 says what does your value of t represent? Now the value of the intercept I, not t, represent mass of the spiral spring. And don't forget m0. Don't forget that I stated earlier that where we were asked to the mass, the spring without the mass, we should measure our p0. Now, for you to have a value at that particular time, it means that the spring itself has a mass. But in the course of the experiment, we did not account for that very mass, or we did not even add the mass to that very to the masses that were given to us, like these masses that were given to us. Okay. Now let me explain it a very simple thing. For example, if the spiral spring mass is 5 grams, it means that if I'm adding 50 grams load to that spiral spring, total mass or total weight that is stretching that spring is supposed to be 55. Then if I'm adding 100, I'm supposed to get 105. All right. But for some reasons, the spiral spring was assumed to be massless. All right, was assumed to be massless. So there wasn't any form of adding of the spring. But at the end of the day, like I said earlier, we are going to account for it, and that is exactly where we are right now. Okay, so we are going to account for that spring. Now let's go back to the equation. Okay, this equation we have, the equation that was given from the background study, from the theoretical study, and that is t equals to 2 pi square root of m plus m naught all over k1g or kg. All right, if you look at this equation, it's also similar to that we have in pendulum, but that of pendulum is t equals to 2 pi then square root of L over g. Then if you go to compound pendulum, we have that of t equals to 2 pi into L squared plus k squared all over what? GL, where k is the radius of gyration. And the k that we have here is not radius of gyration, rather it is what? The spring constant. Okay, the spring constant. Now when you go further, if you look at the equation they've already done, you notice that the k1 represents a different thing entirely. So we'll look at that. So when you transform the equation, first of all, you have to square both sides. Now, what are we actually doing? We want to relate this equation to equation of a straight line. All right? We plotted a graph of m against t squared. So we are going to make m, not m naught. M and m naught are not the same. M naught, we will get that. Then m is the normal mass that was given to you. So if we make m subject formula, we are going to get this. All right, first we square both sides. Then later on we now cross multiply or multiply through by k1g, and then divide through by 4 pi square, and then we have this very section. Now the next step down is we move our m naught to the left hand side to remain only m, since we are making m subject formula. So that gives us the equation 2 we have there. So by comparison with y equals to mx plus c, we now have the information down here. So the intercept becomes, if you watch that, the intercept is what? Negative. Compare that. The c correspond to m naught. Okay, let me start from the left hand side. The m correspond with the y, meaning that the m was on the y-axis. Then the t square correspond with the x. Then behind the t square we have k1g over 4 pi square, and behind x we have m. Let's not confuse these two m. The m in the main equation is the mass, while this m here is the gradient or the slope of the graph, which is general equation of a straight line. Then if you look further, you also see c, letter c, on the second equation, the equation of a straight line. That c corresponds to m naught minus m naught. So this shows that the intercept of this very graph is what? Negative. That was why you saw me explaining this. That's why I say intercept negative. This has already been done before now, so that's why I'm here to guide you. All right. So I think that's it now. Yeah. So intercept is negative. So then I say, what does the intercept represent? It represents the mass of the spiral spring. Mass of the spiral spring. All right. Now sometimes even the spiral spring may have a scale pan attached. So at times it could also be mass of the spiral spring alongside with that of what? The scale pan. That is scale pan, which is used to contain the weights that will be added to the system. Now we have here, it said okay, now if you compare that slope, it's now k1 4 pi square g. Okay, that's your slope there. Okay. All right, so that's our slope there. Of course we have this. So question 4 says, let's see question 4. So calculate a force required to expand your spring a distance of 10 cm. Okay, so we take question 4. Now we said we are using the formula slope equals to k1g over 4 pi square. Why? Now k1, if you look at the derivation here from the beginning, if you go through these parts, you can learn more from there how k1 was derived. So you can go back there on your own to check how k1 was derived. Okay, so if you look at these very parts section, you see that k1 is actually m over e times g, which is the mass, the slope of the first graph times g. So we'll now come here and then we'll call it k1. All right, no, like if you make from your Hooke's law, which is F equals to ke, when you make a subject formula, don't forget that your F is now mg, then you'll get this. Now where m over e is now the k1. All right, so the k1 times e. Now the k1 times e if you multiply it down there, you are going to get S1 times G times E. So that's it. So you can then insert your value. Then you have to convert the 10 cm given to you to meters, so I'll be able to get 16.34 Newton. So I think this is all we have for this section. Now the question 5 is just proving. Question 5 is proving. You are asked to show that total energy of any floating body is proportional to the square of the amplitude. So if you check your Phys 101 textbook under simple harmonic motion or so, chapter 8 or 9, you'll find this very proven there. Okay, so but if you look at it very well, see that total energy in a oscillating system is a combination of kinetic energy and potential energy. And kinetic energy is actually given as half mv square, which is equation 1. Then whereas the potential energy is given as half ks square. Now potential energy is also the same as the energy stored in the spiral spring, which we all know as half ke square or kx square. So that's what we have. So if you rearrange the equation, you can also find your mgh that you are very familiar with. But for a spring, the potential energy is half kx square. All right. Now, the displacement of any vibrating object, which is like a waveform, all right, oscillatory motion, vibratory motion, they are periodic motion. So if you go into circular motion and simple harmonic motion, the concepts are almost the same, all right. So the equation that surrounds or that guides such motion of a wave or vibrating object is given as um, S equal to a sine phi, where we can also have a sine omega t plus phi. Now from here now we can actually get our velocity by differentiating that very function, that equation 3, with respect to t. So if you differentiate that, just like a chain rule, you differentiate omega t, you get omega, then you bring it out, multiply it by a, then differentiate your sine, you get cos, then you repeat that equation to get equation 4. All right. Now put that equation 4 into your equation 1, that's your kinetic energy formula. You end up getting this after expansion. Then yeah, so we do that. Now again, you also put the equation 3 into equation 2. Put equation 3 into equation 2, you get the potential energy formula, and you can see that they are all related. Now from what we have here, the two equations, the equation 5, let's go back. Equation 5 is given as half ka square cos square omega t plus phi. All right, because k is equal to m omega square from the real definition, from the normal definition of a relationship between a k mass and omega and angular frequency. So by the time you do that, the PE and the KE will have similar arrangement. So by the time we made earlier, okay, you are going to now have half K A square, all right, being common, then into sine square omega t plus phi plus cos plus phi. And in our trigonometry basic mathematics, sine square A plus cos square A equal to what? 1. So at the end of the day, the cos square and the sine square will disappear, leaving you with half Ka square. So you can actually relate those to leaving the constant of the equation. So this is all about M9. This is all about M9. If you have a question or you have any area you are not cleared, please drop it on the comment section. And not just that, try to also share this link, the modulo solution. I'm here to guide you by the grace of God. I'm also working in the University of Port Harcourt, and trying to also help our students also to get the best. The year 1 students. Of course, the year 1 is foundation, is fundamental, and many students, because of the various schools that many of you attend, and then we're not opportune to have access to your lab or to even do some of these things, so it becomes a problem when it comes to university. And sometimes some students will expect, they will say, they are not teaching us. Nobody teaching you physics practical. They assume that you know it, and they are working based on your O level. Of course, these are O level questions. Even those in the WAEC, those who write WAEC, the only difference is just the question they have at the end of the day. The setup, some of the questions are the same. All right, so there's not much different there. So they assume that you know everything, and of course, which is true, you're supposed to know everything. But we understand the fact that some of you didn't have opportunity to learn some of these things, so that's why we are here for you. So please help us to share, help me to share this link, video link, to share it to your departments, to your friends within and outside campus, other universities, or every federal government universities, and of course state university, private universities who do something related to that area. They need this video, so please share to them. Okay, it's not just Uniport. I'm just using Uniport as a case study. Please share with them, and then subscribe to the channel. Please don't just watch the video, just click on the button, okay, just subscribe, and then turn on notification bell so that once I drop a video, you'll be there to get the video immediately I share it. Then don't forget to join my WhatsApp groups where you'll be asking questions and then solving problems as we move on. All right, so I'll be ending the live now, and I will want I will what is it? I would like to put some this thing. We'll continue in the next class, like the next other practical. So you can be checking other videos while they are coming step by step. All right. So thank you. I wish you all the best.